Imagine that there is only one copy of a certain diary in the entire world. It records whom one person loved, what they feared, which choices they made, and why they later regretted them. There is no backup anywhere. What happens if we throw that diary into a fire? The paper blackens and the sentences disappear. But a physicist would not immediately say that the information has been completely destroyed. The atoms in the paper become ash and smoke. Energy spreads through light and heat. If we could know every microscopic fluctuation of the flame and every motion of the surrounding air, then in principle traces of the initial state would remain dispersed through the wider universe. Reconstructing the diary would be practically impossible, but nature may not have deleted it in a fundamental sense. Now imagine throwing that diary into a black hole. It crosses the event horizon. From outside, we can never retrieve it or send a beam of light to read its pages again. If the black hole remained forever, we might still say that the information was trapped somewhere inside. But black holes may not last forever. Stephen Hawking discovered that when quantum fields are considered, a black hole emits extremely faint thermal radiation and slowly loses mass. After an unimaginably long time, it may shrink and eventually evaporate completely. Then where is the information in the diary? The diary is gone. The black hole is gone. All that remains is Hawking radiation, apparently emitted almost at random according to a temperature. If that radiation carries no record of the diary's sentences, the universe has not merely destroyed an object. It has severed the information that once connected the past to the present. A black hole would then be more than an object that swallows matter. It would be a cosmic eraser capable of deleting the past itself. This is the black hole information paradox. To understand it, we must first ask why a black hole emits anything at all. In classical general relativity, the event horizon is a boundary of no return. Light and matter that cross it cannot come back out. A black hole appears to be a perfectly dark prison that absorbs everything and releases nothing. In quantum theory, however, the vacuum is not simply an empty stage. Quantum fields fluctuate, and even the meaning of a particle can depend on the observer and on the structure of spacetime. Near a black hole, where spacetime is strongly curved, the state that a distant observer calls empty is not defined in exactly the same way as the natural vacuum near the horizon. Because of this mismatch, a distant observer detects particles coming from the black hole. This is Hawking radiation. A popular picture describes a particle and antiparticle pair appearing near the horizon, with one falling inward while the other escapes. It is a useful intuition, but it is not the precise calculation. The deeper point is that quantum field modes become mixed in curved spacetime, so a state that looked like vacuum in the past can appear to contain particles to an observer in the future. Hawking radiation has a temperature determined by the black hole's mass. Large black holes are colder. As a black hole becomes smaller, it grows hotter. The outgoing radiation carries energy away, so the black hole loses mass and its evaporation gradually accelerates. The problem is that the radiation appears nearly thermal. When a lump of coal glows, its light can tell us its approximate temperature. But that thermal glow does not obviously reveal which tree the coal came from, who touched it, or what words may once have been written on its surface. Likewise, in Hawking's original calculation, the radiation seems to depend only on a few macroscopic properties of the black hole, such as mass, angular momentum, and charge. If a diary, an encyclopedia, a piano, and a human body entered black holes with the same mass and charge, the final thermal radiation would appear unable to tell us which one had fallen in. Why is this more serious than simply not knowing the answer? In quantum mechanics, information does not mean only words in a book. It means every distinction that can separate one complete quantum state from another. The time evolution of a closed quantum system is said to be unitary. In simple language, two different initial states must not be crushed into exactly the same final state. Pour 2 bottles of perfume into a large swimming pool. The molecules spread and become hopelessly mixed. In practice, we cannot track which molecule came from which bottle. But if we knew every molecular position and motion perfectly, the distinction between the two initial states would remain encoded in microscopic correlations. The information is scrambled, not erased. Burning paper is similar. Recovery is unimaginably difficult, but from the viewpoint of the complete quantum state, information has moved into correlations among light, heat, ash, and the environment. Black hole formation and complete evaporation seem different. If a pure initial quantum state becomes an ordinary thermal mixed state, distinct pasts merge into the same future. Even complete knowledge of the future would not let us distinguish how the process began. This is not merely computational difficulty, it is a breakdown in the predictive structure of physical law. Hawking once argued that this loss of information genuinely occurs. Many physicists resisted because abandoning quantum unitarity could destabilize much more than black hole physics. The interpretation of probability, microscopic causality, and the consistency of quantum theory might all be affected. Don Page then asked a crucial question. If a black hole evaporates without destroying information, when should that information begin to appear in the Hawking radiation? At the beginning, the outgoing radiation can look almost thermal. Each emitted quantum is entangled with degrees of freedom associated with the remaining black hole, so the entanglement entropy of the collected radiation rises. Here, entropy does not simply mean disorder. It measures how much information about the full state is missing when we look only at the radiation. But if evaporation is unitary, that entropy cannot rise forever. After roughly the middle of the evaporation process, newly emitted radiation must develop subtle correlations with the radiation that escaped earlier. Only then can the complete radiation state become pure when the black hole is gone. Plot the radiation entropy over time, and it first rises, reaches a peak, and then falls. The resulting mountain-shaped graph is called the Page curve. The point near its summit is the Page time. The curve tells us something remarkable. A young black hole behaves like a vault that hides information. Once it becomes old enough, it may act more like a mirror, returning even newly added information relatively quickly through correlations in the radiation. Hayden and Preskill developed this black hole mirror idea using quantum information theory. This does not mean that a sentence from the diary emerges written on one Hawking photon. The information may be encoded in extremely complicated, non-local correlations among enormous numbers of radiation quanta. Each quantum looks random on its own, while the entire radiation pattern can still form a pure state. It would be like tearing a novel into individual letters, scattering them across the world, and then hiding the story not in their order or location, but in trillions of relationships among them. The Page curve tells us what unitarity requires. But can gravity itself produce that curve? For decades, this was one of the hardest questions in theoretical physics. A powerful clue came from holography. The holographic principle suggests that information in a gravitational volume may be represented by a quantum theory living on a lower dimensional boundary. In the IDS-CFT correspondence, gravity in certain anti-de Sitter spacetimes is proposed to be equivalent to a unitary quantum field theory on the boundary. If the boundary theory is unitary, then the equivalent black hole process should not fundamentally lose information. This became powerful theoretical evidence in favor of information preservation. Yet, knowing that information must survive is not the same as knowing how it emerges. Trying to explain how information behind an event horizon becomes encoded in outside radiation leads to another conflict. Black hole complementarity proposed that the outside observer and the falling observer may use different descriptions without creating a contradiction that any one observer can test. To the outsider, information can be processed near the horizon and later emerge in radiation. To the falling observer, nothing unusual happens at the horizon, and the information continues inward. The Firewall argument disturbed this peaceful compromise. For an old black hole, a late Hawking quantum must be entangled with the early radiation if the total information is to be preserved. At the same time, if the horizon is to look like a smooth quantum vacuum, that outgoing quantum must also be strongly entangled with a partner mode inside the horizon. But one quantum system cannot be maximally entangled with two independent systems at once. This is sometimes described as the monogamy of entanglement. At least one of three ideas must therefore be modified: the unitarity of Hawking radiation, the validity of local effective field theory near the horizon, or the claim that a freely falling observer experiences nothing special at the horizon. If the entanglement across the horizon is broken, the smooth vacuum may be replaced by a wall of extremely energetic quanta, a firewall that burns up the falling observer. But that clashes with the general relativistic expectation that the horizon of a large black hole should be locally unremarkable. Must we set the horizon on fire to save information? Or have we divided the inside and outside in the wrong way? One of the greatest recent advances begins with a surprising answer: the island formula. In Hawking's original calculation, we collect the radiation that reaches the outside and calculate its entropy. The result keeps rising and does not follow the Page curve. But in a gravitational system, the classical division of space into inside and outside may be insufficient for calculating fine-grained entropy. When quantum extremal surfaces and generalized entropy are included, part of the black hole interior can eventually become part of the region used to calculate the entropy of the outside radiation. That interior region is called an island. Early in the evaporation, the calculation with no island dominates, and the radiation entropy increases. Near the page time, another contribution becomes more important. When the island is counted together with the radiation, the entropy turns around and begins to decrease. The unitary page curve emerges. In the gravitational path, integral, new geometric saddle points known as replica wormholes connect different replicas used in the entropy calculation. Regions that appeared separate in a classical picture are reorganized into a single informational domain for the purpose of quantum entanglement. This does not mean that a classical signal travels faster than light from behind the horizon. It means that after the page transition, part of the black hole interior belongs to the entanglement wedge of the radiation and can, in principle, be reconstructed from the radiation as a whole. The island formula and replica wormhole calculations are remarkable because gravity itself now produces a page curve. A study published in 2026 applied the island rule to a dimensionally reduced model of an evaporating Schwarzschild black hole and again obtained a unitary page curve. But it would be premature to declare the paradox completely solved. The most controlled calculations are performed in holographic settings and in simplified or lower dimensional models of gravity. We still do not possess a complete description of the final evaporation of a realistic, four-dimensional, astrophysical black hole, the resolution of the singularity, or the exact microscopic map from interior states to outgoing radiation, and preserving information is not the same as reading it. The information in Hawking radiation may be scrambled beyond imagination. Black holes are believed to be among nature's fastest scramblers. If the information is encoded in high-order correlations spread across all the radiation, decoding it may require a quantum computation that takes far longer than the lifetime of the black hole itself. Recent research explores this question through computational complexity and quantum resources. A 2026 study of toy models of black hole evaporation found that a measure of non-classical computational complexity in Hawking radiation can become extremely large after the page transition. This suggests that information may emerge in a form utterly unlike an ordinary message. The universe may not forget. Yet to an observer, the information may remain an unreadable code forever. So where does physics stand today? Many theoretical physicists expect a complete theory of quantum gravity to preserve information. Holography, the page curve, and the island formula strongly support that direction. But questions involving firewalls, interior reconstruction, state dependence, and the end point of realistic evaporation remain open. Competing ideas also continue to be studied. Perhaps a tiny remnant stores the information. Perhaps string theory fuzzballs replace the traditional smooth interior with enormous families of horizon-scale microstates. Perhaps space-time locality itself must be modified. Deriving the page curve is a major milestone. It does not yet mean that we understand every microscopic degree of freedom, carrying the information or the full mechanism by which those degrees of freedom become radiation correlations. At this point, let us take one further step and consider the IG, or information gauge, perspective. I must emphasize the boundary. Hawking radiation, the page curve, holography, the firewall debate, and the island formula belong to established or actively developed quantum gravity research. The IG interpretation that follows is an unverified hypothesis, extending these ideas into the language of information connections. IG must not claim to replace the island formula. In the IG perspective, information is not treated only as a number stored inside an object. It gains physical meaning through relationships that distinguish and compare states. Imagine black hole formation and evaporation as one long information loop. The collapsing matter and its quantum state, horizon degrees of freedom, the interior, Hawking radiation, and a distant detector become information nodes. Entanglement and correlation among them become information links. The rules that carry and compare informational references between states become an information connection. Information moves from collapsing matter into the horizon and interior, and is later reorganized into correlations in Hawking radiation. The entire process, from preparation to disappearance and possible reconstruction, can be viewed as a closed informational path. If transporting a state along different informational paths does not lead to exactly the same final comparison, information space could be said to possess curvature. If a relational residue depending on the initial preparation remains after the full cycle of formation and evaporation, it could be interpreted as information holonomy. Standard unitary evolution already requires differences in initial states to survive in correlations within the final radiation. If IG merely says that information remains in correlations, it adds nothing new. An independent prediction is required. Consider two processes with the same total energy and entropy, and the same low-order observables in the final density matrix, but with different causal orders or preparation histories for the injected information. IG could ask whether higher-order radiation correlations retain an additional shared phase or residual pattern depending on that preparation path, even where a baseline model predicts no difference. We cannot realistically perform such a controlled experiment with an astrophysical black hole, but analog horizons in fluids or condensed matter, evaporating quantum circuit models, random quantum systems, and superconducting qubits allow researchers to control information injection and recovery. Under identical energy and noise conditions, we could change only the order in which information is injected, and then test for reproducible differences in recovery delay, mutual information, or higher-order correlations. We could also reverse the ordering of an information loop and look for a deviation beyond the symmetry predicted by ordinary unitary evolution. Before calling any anomaly an IG effect, however, we would need to remove thermal noise, finite size effects, imperfect gates, measurement bias, environmental decoherence, and ordinary non-Markovian memory. If every residue is explained by standard quantum mechanics and apparatus noise, the minimal IG model is not supported. If changing the preparation order produces no additional common scaling, the proposed information holonomy has not been observed. Perhaps this is the most important lesson of the black hole information paradox. What we cannot read is not necessarily the same as what does not exist. Reconstructing a burned diary is practically impossible. That does not prove that its past has been fundamentally deleted from physical law. A black hole may be similar. Instead of vanishing, information may be translated into the most complicated relationships we can imagine. Let us return to the diary. It crossed the event horizon, and the black hole evaporated after an immense span of time. Only faint radiation remains outside. Each radiation quantum appears to be meaningless noise. But if some observer could see the complete quantum state of the universe, perhaps they would discover traces of the lost sentences in correlations among countless particles. The letters no longer exist in the shape of letters. The memory no longer survives in a form we recognize as memory. What remains may be a network of relationships that still distinguishes one past from another. Human memory and quantum information are not the same thing. Forgetting a person and preserving quantum unitarity belong to very different levels of description. Yet they meet before one philosophical question. If no one remains who can read a trace, does that trace still exist? Physics answers cautiously. Difficulty of observation is not, by itself, proof of non-existence. A black hole may not be the universe's ultimate eraser. It may instead be the darkest translator, converting a once clear past into a code of correlations that is almost impossible to solve. If the universe does not permit complete oblivion, then disappearance may not be the deletion of existence. It may be a transformation so deep that we can no longer recognize the information's new form. And the black hole information paradox continues to ask us, does the universe truly remember? Or have we simply not yet learned the language in which it refuses to forget? If you enjoyed this journey, please subscribe and like the video. Together we will keep following the deeper questions hidden behind the world we think we already understand. This has been ThothSaem's Science Catch.